let's talk about counting rules. Now, we have been talking about probability, and in classical probability, the way you calculate the probability of some event occurring is by counting the number of ways that event could occur and then dividing by the total number of possible outcomes to your probability experiment. So that's assuming all the outcomes are equally likely. But sometimes it can be tricky to find these numbers, to count how many ways an event could occur, or how many ways a probability experiment could turn out. So that's what we're going to be talking about here. How do you count how many ways something can happen? And we're actually not going to be counting things 1, 2, 3, 4, 5, because in the situations we're going to be talking about, there's going to be lots and lots and lots of ways, and we want to be able to calculate or figure out how many possibilities there are without actually going through them individually one by one. So we're going to be investigating questions of how many ways are there of doing something? How many possibilities or arrangements or outcomes or different ways of doing something are possible? For example, if you ever play poker, you may have wondered, how do we know the probability of getting certain kinds of poker hands, like a full house or a royal flush or three of a kind? Well, to calculate those probabilities, if we could calculate how many ways there are of picking any 5 cards, and then out of all those ways, how many of them are there where you actually do get a royal flush or three of a kind or whatever poker hand you're talking about? Or what about the lottery? What's the probability of winning the lottery? Well, it depends on exactly how that lotto game works, but lots of them work where you have to pick like 6 numbers from 1 to 50 or 5 numbers from 1 to 45 or something like that. And to win the jackpot, you have to match all the numbers you pick in any order. So the probability of doing that, you have to know, okay, how many different ways are there of picking 5 numbers from 1 to 45 or whatever the possibilities are. So let's start with a simple question. How many ways could you pick a letter from A through T? Well, how many choices are there? There's 20 letters from A through T. A is the first letter of the alphabet, B is the second, all the way up through T is the 20th. So if you're picking one of those letters, you got 20 to choose from. Now, how many ways could you pick a letter from A through T and a number from 1 through 30? So there's 20 choices for the letter. There's 30 choices for what number you pick. At first you might think, well, add those together. 20 plus 30 equals 50. But that's not the answer to this question. If I said, how many ways could you pick one of those letters or one of those numbers, there would be 50 possibilities. But you're picking one of the letters, and then you're also picking one of the numbers to go with it. So your final choice is made up of a letter and a number together. If you want to picture this, imagine an auditorium where there are 20 rows of seats, each with a letter, A through T, and then there are 30 seats in each row. Seat 1, seat 2, seat 3, all the way over to seat 30. How many seats are there? So 20 rows, 30 seats in each row. That's A1 through A30, B1 through B30, C1 through C30, and so on. 20 rows with 30 seats in each row, that's 600 seats. If you were printing up a ticket for each seat, you would have to print up 600 tickets. So this is an example of the fundamental counting rule that says that to find the number of ways a sequence of events could occur, or the number of ways a sequence of choices could be made, you would do that by multiplying together the number of possible ways each individual event in the sequence could occur, or each choice in the sequence could be made. So the number of ways to do A and B equals the number of ways to do A times the number of ways to do B. Like the number of ways to pick a letter and a number equals the number of ways to pick the letter times the number of ways to pick the number. And what if you had shows going 7 days a week and you were printing a ticket for each seat for each day of the week? How many ways could you pick a letter from A through T, a number from 1 through 30, and a day of the week from Sunday through Saturday? Now let me remind you that anytime I ask an example question like this, if you want to try to figure it out for yourself before I give you the answer, you're welcome to pause the video for as long as it takes you to come up with your own answer. So now I'm going to give you the answer. It's 20 times 30 times 7, which if you multiply it out gives you 4,200. 20 ways to pick the letter times 30 ways to pick the number times 7 possibilities for the day of the week. Next example. Suppose you have 4 shirts, a red one, a green one, a yellow one, and a white one, and 3 pairs of pants, blue, black, and tan. How many different outfits could you wear? So think of this in terms of making a series or sequence of choices. You're picking one of the shirts and one of the pairs of pants. So there are 4 possibilities for the shirt times 3 for the pants, so 12 different outfits. The red shirt with the blue pants, the red shirt with the black pants, the red shirt with the tan pants, the green shirt with the blue pants, and so on, through all 12 possibilities. Or are there even more possibilities? You might be thinking, well, if I have 4 shirts, I could wear the red shirt, I could wear the green shirt, the yellow shirt, the white shirt, or I could just go shirtless, wear no shirt at all. So there's 5 possibilities for what you wear on top if nothing at all is one of the possibilities. And if you're allowing yourself to go pantsless, there are 4 possibilities for what you wear on the bottom part of your body. So in that case, there would be 5 times 4, or 20 possible outfits, one of which is where you don't wear any shirt or pants. You just run around naked. Next example. From a group of 5 people, let's say Al, Brenda, Carl, Don, and Ellen, how many ways could a president and vice president be selected? So we're making 2 choices. We're picking a president and a vice president. For the president, we have 5 people to choose from. Then for the vice president, that can't be the same person as the president. So when we're choosing a vice president, there's 4 possibilities. So altogether, that gives us 5 times 4, or 20 ways of choosing a president and a vice president. The president could be either Al, Brenda, Carl, Don, or Ellen. And then the vice president could be any of the other 4. So if the president is Al, you could have Al with Brenda, Al with Carl, Al with Don, or Al with Ellen. So altogether, there's 20 ways of having a president and a vice president. Next example. Ed likes peanut butter and jelly sandwiches, but he also likes variety. He doesn't like the exact same sandwich every day. How many different sandwiches can he make if he has 2 kinds of bread, maybe white and wheat, 2 kinds of peanut butter, say smooth and crunchy, and 5 different kinds of jelly? So we're making a sequence of choices here. We're picking a kind of bread and a kind of peanut butter and a kind of jelly. So the number of ways of making that sequence of choices would be 2 times 2 times 5, which comes out to 20. How many different sets of 3 initials are there? Well, let's see. we're making a sequence of choices, or we have a sequence of possibilities. First initial, second initial, third initial. How many possibilities are there for what that first initial is? Well, there are 26 letters in the alphabet, so there's 26 possibilities for what that first letter is. And then there's 26 possibilities for the middle initial and 26 possibilities for the last initial. So 26 times 26 times 26 comes out to 17,576 different sets of 3 initials. Now, how many are there if no letter can be repeated? So like if your first initial is W, we can't use W for the second or third initial. Now, there's still 26 possibilities for the first initial, but if the second one can't match the first one, there's 25 possibilities for what that second initial could be. And then how many possibilities are there for the third one? 24. So when we multiply 26 times 25 times 24 comes out to 15,600. Okay, next example. Suppose a state is designing a special license plate which will consist of a letter followed by 3 digits, like for example S317 or W880. So you're going to have a letter and then a digit and a digit and a digit. How many different plates like that are possible? Answer, 26 times 10 times 10 times 10. 26 possibilities for the letter, 10 possibilities for the first digit, because it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. 10 possibilities for the second digit, 10 possibilities for the third digit. We multiply how many possibilities there are for each one, and it comes out to 26,000. How many plates are possible if the first digit can't be a 0? Now the answer is 26 times 9 times 10 times 10. There's only 9 possibilities for what that first digit is if it can only be 1, 2, 3, 4, 5, 6, 7, 8, or 9. It can't be 0. So now when we multiply, we get an answer of 23,400 possibilities. How many plates are possible if no digit can be repeated? Well, there's 26 possibilities for the letter, 10 possibilities, we're back to all 10 possibilities for the first digit, 9 possibilities for the second, and then 8 possibilities for the third, because that third digit has to be one of the 8 digits that we haven't used already for the first or second. So 26 times 10 times 9 times 8 comes out to 18,720. Suppose you have to pick a 6-letter password. How many possibilities are there for that? So if each of the 6 letters could be any one of the 26 letters of the alphabet, there's 26 possibilities for the first letter, 26 for the second, and so on. So altogether that's 26 times 26 times 26 times 26 times 26 times 26, or 26 to the 6th power, which comes out to be 308,915,776 possibilities. Now that sounds like a lot, but if you had a computer that could run through 1 million possibilities each second to try and guess your password, it could run through all of those possibilities in 308.9 seconds, which is just over 5 minutes. So maybe that's not secure enough. Maybe we need at least an 8-letter password. How many 8-letter passwords are possible? Well, that would be 26 times 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 26. That comes out to 208,827,064,576 possibilities. That same computer could run through all of those in just over 58 hours. Now, what if instead of just using letters, you could use lowercase letters or uppercase letters, which count differently, or digits or symbols? I'll tell you that in the next video.